All right, so let's go ahead and look at section 3.7, improper integrals. And the first thing I want to do is give you an idea for what these things are. So I think a really good example of this would be if I, write down, for example, an integral where one of my limits of integration is infinity, right? So something like the integral from 1 to infinity of like 1 over x squared dx. Okay. And if I look at that on a graph, okay, so here's the graph of y equals 1 over x squared. And the integral from 1 to infinity is just going to say, okay, start here at 1 and just find all of this area going on forever. Now, it is certainly possible that if I start adding up these bits of area, since I'm adding up forever, that amount of area will just keep going up and up forever. And then what happens is I get what appears to be an infinite amount of area. And in that situation, we say that the integral will diverge. Okay, so integrals, remember, don't exactly have to be area, but this is a good way to start thinking about things and to kind of get some context. Okay, so an improper integral is an integral where either we have infinity as one of the limits of our integration, or if the function is not continuous that we're integrating over. So either one of the limits are infinite, so that could be infinity or negative infinity, or it might be that the function is not continuous on our the interval that we're integrating over. Okay. So let me show you how we're going to deal with this, and we're going to start with this first case where you have limits of infinite limits of integration. It's actually a little bit simpler, and we'll do this first example. The way that I want to think about this is if I start off with my graph, and I'm only going to draw the right-hand side of the graph here. Okay, I could take an integral from 1 to some finite number, right? Maybe call it a. Actually, I'm gonna call it b. I'll explain why in a second. Right, so I could find that area, and that's a regular integral. I can find that, right? I could pick different numbers for b, maybe 10, maybe 100, something like that. And what I can do is I can say, well, what happens if I move this b around? And then maybe I can say, well, let's take a limit as b goes to infinity. Okay, and that'll stretch that out and give me the full business. Okay, so what we do is we say the integral from 1 to infinity of my function is going to be the limit as b goes to infinity of the integral from 1 to b. Because what I'm going to do is when I integrate from 1 to b, I have a regular finite integral. Everything works fine, and I can do that integral. And then I'm left with something that is a number that depends on b, or essentially a function of b. And so then I can take a limit of a function, and that's not a problem, right? Okay. So that's kind of the idea behind improper integrals, right? We turn it into a proper integral and take a limit as that piece goes off to infinity. Okay, so let's look at how that works. So let's look at our example, the integral from 1 to infinity of 1 over x squared dx. Okay, and what I'm going to do is I'm going to say, well, I'm going to write that as a limit as b goes to infinity of the integral from 1 to b. And I'm going to rewrite 1 over x squared as x to the negative 2 because I'm going to use the power rule to integrate that. Okay, so the limit is going to just hang out for a bit. I go ahead and integrate x to the negative 2. I add 1 to the power, divide by the new power. Okay, then we plug in. So x to the negative 1 over negative 1 is the same as negative 1 over x So I have negative 1 over b minus negative 1 over 1. So I have the limit as b goes to infinity of negative 1 over b plus 1. And now I go ahead and find the limit. Okay, and I know from back in Calculus 1 that if I had a limit where x, or in this case b, is going to infinity, and I'm dividing by that, then that piece is going to go to 0. So this is just 0 plus 1, or 1. Okay, so that's it. We have now found the area of a region that's infinitely long. Okay. So the integral from 1 to infinity of 1 over x squared dx is equal to 1. All right, let's try another one. Let's try the integral from 1 to infinity of just 1 over x. See if that makes a difference. Okay, maybe just to give you some perspective, right? If I go ahead and graph this on my calculator, start with 1 over x squared. That'll be blue, and then the one we're currently doing, 1 over x, is in red. Okay. They're not very different. I mean, they are like on the left-hand side, but if I go from 1 to infinity, so if I change my zoom window and I start at an x value of 1, and we'll just go up to 10, that's fine. These two functions look pretty close to one another, right? And if I want to look maybe a little bit more closely, let's have our y values, come in a little bit tighter. Okay, I can see that, yeah, the red function is a little bit taller, but same general shape. So it feels like it shouldn't really make much of a difference. I'm going to have maybe a little bit more area, but things should otherwise work out very similarly. So let's see how it goes, right? So I'm going to take the limit as b goes to infinity of the integral from 1 to b, 1 over x dx. For 1 over x, I don't like to write it as an x to the negative 1, because as a 1 over x, I feel like I'm more likely to remember that this is a log rule, not a power rule. So when I integrate, I get ln of absolute x going from 1 to b. The absolute value is not necessary because these are positive numbers. So we have ln of b minus ln of 1. Ln of 1 is 0. But if I look at my natural log function, as b goes to infinity, ln of b goes to infinity. And I have to be careful about writing stuff equal to infinity. Now, we have done that with limits in the past. But one of the things that we want to remember is that when a limit is equal to infinity, that really means that the limit doesn't exist. Now, when we were in Calc 1 and we had limits, in particular when we were looking at graphs, we would write a limit equals infinity, and usually that meant that we had like an asymptote or something, right? There was something physical in the graph that meant. But in this case, when we're looking at area, we don't want to think about it as being infinite area. What we're going to do is we're going to have a different term for this. We're going to say that this integral diverges. So if the limit is infinite, we say that the integral diverges. Highlight the diverges here. Okay, so for this example, we would say it diverges. So it turns out that that little bit of extra height is enough to make the area essentially infinite, whereas this one that comes down and hits close to the axis, I'm adding up much smaller pieces, and the amount that I'm adding up becomes small enough, quickly enough that it doesn't matter. Now, we'll talk about adding stuff up in the next chapter, but for right now, we can say, all right, that amount of area is going to be finite for the x, 1 over x squared function, but since it goes to infinity for the 1 over x function, it diverges. All right, let's look at another example. Let's suppose I have an integral from negative infinity to positive infinity. And we're looking at x e to the x dx. Okay, here both of my limits of integration are infinite, and that's fine. There are I guess, two different ways to handle this. What we'll do is we'll just kind of go with the safest way to do this. I don't want to have two different problems parts on my integral. So I'm going to break this up into two, right? So what I'm going to do is I'm going to begin by saying, okay, this is the integral from negative infinity to 0 of x e to the x dx, plus the integral from 0 to infinity of x e to the x dx. Okay, and now for each one of these, I only have one limit of integration that's infinite, and that way it's, we won't run into problems. Okay, so I'm going to treat each one of these separately, right? Work out each integral separately. Okay, if one of them diverges, then the whole thing diverges. Okay, so the only way that I get a value out of this is if both of them come out to be a finite number. All right, so let's look at the first one. So the integral from negative infinity to 0 of x e to the x dx is going to be the limit as a goes to negative infinity of the integral from a to 0 of x e to the x dx. Now, there's not a set rule on how to do this, but I typically like to, when I'm working with my limits of integration, I replace an upper limit of integration if it's infinite with a b and a lower limit with an a, and that's just how I do things, but that's not really necessary. In the book, because you're only ever working with one infinite limit of integration at a time, they just pick another dummy variable like, say, t, whatever you're comfortable with. But I'm just going to replace the lower limits with an a and the upper limits when I do that with a b. All right, now to work out this integral, to integrate x times e to the x, because that's a product, I'm going to want to use integration by parts. So I'm going to work out the integration by parts separately. So let's find the integral of x e to the x dx using parts. And I don't like to do definite integrals with integration by parts. I like to work out what the integral is first and then worry about the limits of integration. Because with all the different variables floating around, it can be very confusing what to plug in. So this is, I think, the safest way to avoid problems. So I'm going to let u equal x and dv equal e to the x dx. So when I differentiate u, right, du dx is just 1, so du is dx. When I integrate e to the x dx, I'm just going to get e to the x. So this is going to be uv minus the integral of v du. uv is x e to the x minus the integral of e to the x dx. And the integral of e to the x dx is e to the x. Okay, I should write a plus c, but I'm not going to because I'm going to plug this into a definite integral in the next step, so it's not really necessary. Okay, so this is equal to the limit as a goes to negative infinity of x e to the x minus e to the x evaluated from a to 0. So I have the limit as a goes to negative infinity of 0 e to the 0 minus e to the 0 minus a e to the a minus e to the a. Okay, 0 times anything is 0, so this part is going to be 0. E to the 0 is 1, so I have a negative 1. A times e to the a is going to be a little bit confusing, so let's leave that for now. Okay, and then we have the limit as a goes to negative infinity. Oops, that should be a negative infinity of e to the a. All right. Here's how we deal with confusing limits. First of all, let's check the simpler one, just e to the a. If the a's are confusing, you can think of this as a different letter, right? What if I had the limit as x goes to negative infinity of e to the x? Okay. And if it's a simple function like this, it's sometimes helpful to think about the graph. If I have y equals e to the x, as my x's go to infinity, the y values go up to infinity. As my x values go down to negative infinity, the y values are going to approach 0. Okay, so as a goes to negative infinity, e to the a is going to approach 0. So this limit is 0. Okay. For this limit, the e to the a part I just said is going to go to 0, but the a part is going to negative infinity. We have an infinity times a 0. That's an indeterminate form. So for this limit, use L'Hopital's rule to figure it out. All right. So let's work that out separately. Let's say, all right, I want to take the limit as a goes to negative infinity of a e to the a. And one of the things that we said that we could do when we had a product, L'Hopital's rule always requires us to have a fraction. We can pick one of these things and just shove it into the denominator. So I'm going to take that e to the a and shove it into the denominator as an e to the negative a. Okay, same thing, right? And now as a goes to negative infinity, my numerator is going to go to negative infinity. And I have a negative infinity with a negative on it, so that's a positive infinity. E to the positive infinity is infinity. Excuse me. And so I can use L'Hopital's rule. So this is going to be the limit as a goes to negative infinity. Remember, L'Hopital's rule gives you a new limit. And I look at the derivative of the top and the derivative of the bottom separately. So the derivative of a with respect to a is 1. And the derivative of e to the negative a with respect to a is e to the negative a times negative 1. And now when I try to plug in, negative infinity with a negative on it is positive infinity. E to the positive infinity goes to infinity. So I have a 1 over infinity, which gives me a 0. Okay, so coming back here, we have negative 1 minus 0 minus 0, which gives me negative 1. Now let's look at the other side. Okay, so remember, that was this first piece, the integral from negative infinity to 0. Now let's look at the integral from 0 to infinity. So that's going to be a limit as b goes to infinity of the integral from 0 to b of x e to the x dx. Now, because this is the same inside function, I can reuse some of my work. For example, integrating x e to the x dx, I've already done that. Okay, so I'm going to get x e to the x minus e to the x going from 0 to b. I can save myself a little bit of work there. Okay, so we're going to get b e to the b minus e to the b, and then minus 0 e to the 0 minus e to the 0. Okay, all right. Now, over here, we already worked out something kind of like this. E to the 0 is 1 times 0 is 0. So this is 0 and this is a 1. Okay. On this side, I want to see what happens when I plug in. When I try to plug in, I'm going to get infinity when I plug into b. And e to the infinity is also going to be infinity. Infinity times infinity is not an indeterminate form. That gives me like an infinity. Okay. And then, then I have minus infinity. And I say, well, okay, I don't know what's going on with that. So let's work that out separately. Let's say, all right, what is the limit as b goes to infinity of b e to the b minus e to the b? The problem is infinity minus infinity is an indeterminate form. Okay, so I got to figure out what's going on there. All right, well, to figure out this limit, what I'm going to do is I'm going to factor. I'm going to factor out this e to the b. Oops. And then I have a b minus 1. Okay. I think at this point I can just plug in, because now if I plug in, instead of having infinity minus infinity, here when I try to plug in, e to the b is going to go to infinity. And here I'm going to have an infinity minus 1. Well, infinity minus infinity, I don't know what's going on, but infinity minus 1 is just infinity. And infinity times infinity is infinity. Okay. So then I can say, oh, I got it. This limit is going to be infinity, so the whole integral diverges. Okay. So we have to be a little bit careful, because this looks like a very symmetric looking function. And so you're kind of tempted, when you break this up into two halves, to just evaluate one of the halves and maybe double it or something. You don't do that, right? Unless you can show why they have to be equal. So if you can write down an argument for why the two pieces are equal, then that's fine. But if you can't, then you can't just say, I'm just going to look at one half and double it. You got to be really careful about what you're doing. All right. So all of our integrals so far have had an infinite limit of integration. Let's go back now and look at one where I'm integrating over an interval that's not continuous. So here's our example. Let's look at the integral from, let's say, -2 to 5 of 1 over x dx. Okay. First, I'm gonna show you what this looks like when you do this wrong. Okay, so some people might integrate this and say, all right, I've got a definite integral, let's integrate away. The integral of 1 over x is ln of absolute value of x. Okay, then I plug in, and we get ln of 5 minus ln of 2, right? Or like ln of 5 halves. Okay, and you're done. And that's not correct. Right, so this is approximately 0.916. Okay. Something that I think that sometimes we take for granted is the conditions that we need to use the theorems that we use. When I integrate and I write down an integral, right, as an antiderivative and evaluate at the endpoints, I'm using the fundamental theorem of calculus, right, the fundamental theorem of calculus part 2. And one of the conditions for the fundamental theorem of calculus was that my function is continuous on the interval I'm integrating on. And in this case, that's not true, right? At 0, this function is not continuous, and 0 is in this interval, -2 to 5. Okay. All right. So here's what I want to do. I'm going to break this integral up over the discontinuity. Okay. So I'm going to write this as an integral from -2 to 0 plus an integral from 0 to 5. So I'm putting that bad point at the edge. So we already had examples where that bad point was infinity, because infinity is not a number. But maybe it's just the point where the function's not continuous. But again, if I put it at the edge, then that's something that I can deal with, because conceptually what I'm doing is I'm saying, okay, here I have my 1 over x function. And instead of trying to add up area over this discontinuity, what I'm doing is I'm saying I'm going to be split away from my discontinuity a little bit. I'm going to look at my area up to some point A, and then pick it up again somewhere else at B, add up area. And I take a limit as A gets closer to 0 and B gets closer to 0 separately, and then that's how I figure things out. Okay, so that's the conceptual idea. So then the way that we compute this is just like we did before. I'm going to replace the bad point with a variable and take a limit as that variable goes to 0. Okay, so we're going to take a limit. So let's look at the integral from -2 to 0 of 1 over x dx. That's the limit as b goes to 0 of the integral from -2 to b 1 over x dx, which is the limit as b goes to 0 of ln of absolute x going from -2 to b. So I have ln of the absolute value of b minus ln of the absolute value of -2. And here those absolute values are completely necessary because both b, well, I mean, I should be approaching this from one side, right? Because I should make this a b and an a. Because here my b's are approaching 0, but I'm approaching from the left. So I'm going to put that in there because sometimes that makes a difference. Now, in this case, it doesn't because the b is inside absolute values. So it isn't not going to make a difference, but it might sometimes. Okay. All right, so now I can say, well, what happens if I try to plug 0 into a log function, right? If I take log of 0, I know that's undefined. If I look at the graph of y equals ln of x, as my x values get closer and closer to 0, the y values go down to -infinity. -infinity minus ln of 2 is infinite. So this integral diverges. So the integral from -2 to 5, 1 over x dx, diverges. If one of the sides diverges, it doesn't matter what happens on the other side. The whole thing diverges. Okay.
So what does that mean necessarily, like diverges?
The idea is that if I'm adding up bits of area, instead of that amount of area getting closer and closer to some number, so when I think of a limit, right, as my x value gets closer and closer to the number, a y value has to approach some finite number. Okay, but instead of that happening, the y value is not getting close to some number. It's like moving away from any number that I pick. And so that's where we get that term diverges.
And so that's like an acceptable answer on a test. You can just say that it diverges and then.
That's exactly what we want to say in a test, is that this integral diverges. Yeah.
Okay.
Okay, and then we're going to take this language into the next chapter when we start talking about sequences and series. We'll use these same terms, diverges, and we'll have another one when things work out nicely. We'll say converges, but we won't necessarily be working with integrals. So, but same idea. Okay, now let's go ahead and look at the worksheet. All right, so for this first one, if I look at my function 1 over x cubed, I know that it's not continuous at 0, and 0 is in the interval that we're integrating over. So we have to start by breaking this up. We're going to say, okay, this is the integral from -1 to 0 of 1 over x cubed. I'll write that as x to the -3rd, plus the integral from 0 to 2 of x to the -3rd. Okay, and let's work out those two integrals separately. The integral from -1 to 0 of x to the -3rd dx is the limit as b goes to 0 on the left of the integral from -1 to b of x to the -3rd dx. Okay, let's go ahead and integrate now. Copy down my limit, but I'm not doing any limit stuff. So I add 1 to the power, and I divide by the new power. Okay. And then now what I'm going to do is plug in. So x to the -2 I can write as an x squared in the denominator. So this is like 1 over -2b squared minus 1 over -2 times -1 squared. Okay. As b goes to 0, if I have a 0 in the denominator, I know I'm going to have an infinite limit. Now, when we were working in Calculus 1 with limits, you would look at this and say, well, okay, let's split this into limits from left and right and see does it go to infinity, negative infinity. But remember that here it doesn't matter whether we get infinity or negative infinity or if it splits, right? Because if it's any of the infinities, then it diverges. So we're just done at this point. This one is an infinite limit. So the question is, how do you notice that the integral from -1 to 0? It's because my function's not continuous at 0. That's why I use the 0. I want to put my discontinuity as the edge of my integral so that my limits of integration are where the problem is, not in the middle of the interval. Okay, this is an infinite limit, and the other one's not, right? The other one's just a half, but that doesn't matter. So the whole limit is infinity. So the integral from -1 to 0 of 1 over x cubed dx diverges. So the integral from -1 to 2 of 1 over x cubed dx diverges. Okay, any other questions on this one? All right, let's look at number 4. On number 4, this function is continuous everywhere. That's not a problem, but I have an infinity as one of my limits of integration, so we'll worry about that. All right, so we'll say, okay, this is equal to the integral, to the limit as b goes to infinity of the integral from 1 to b, 1 minus x e to the negative x dx. Okay, and then I need to integrate this, so I'm going to do that separately because I have a multiplication and I think that I'm going to need integration by parts. So for the integral from the integral of 1 minus x e to the negative x dx, we're going to use parts, where my u is 1 minus x and my dv is e to the negative x dx. So du is negative dx, and v is negative e to the negative x. Oops, no dx there. Okay, so the integral of u dv is equal to uv minus the integral of v du. So if I plug in my pieces, I'm going to have 1 minus x negative e to the negative x minus the integral of e to the negative x and then a negative dx. So I have negative 1 minus x e to the negative x minus the integral of positive e to the negative x. And when I integrate that, the integral of e to the negative x is negative e to the negative x, right, plus c. If I distribute this negative, I'll have a negative 1 and a positive x. And the double negative will be plus over here. Okay, so using parts, I figured out my integral. It's x minus 1 e to the negative x plus e to the negative x. Okay, so coming back to my limit problem, when I integrate this, I will get x minus 1 e to the negative x plus e to the negative x, going from 1 to b. So we'll have b minus 1 e to the negative b plus e to the negative b, and then minus 1 minus 1 e to the negative 1 plus e to the negative 1. Okay, the stuff over here on the right I'm not too concerned with. It's definitely going to be finite, although if it doesn't diverge, then I do need to know what number I have. But let's worry about the variable parts over here and see what's going on. So as b goes to infinity, b minus 1 is infinite, but e to the negative b, and e to the negative infinity is going to be like a 0. So here we have what looks like an infinity times 0 situation. That's an indeterminate form. Okay, so I have to figure that out. So let's go ahead and work out that limit separately. Limit as b goes to infinity, b minus 1 e to the negative b. In order to get a fraction, I'm just going to move one of these pieces to the denominator. The exponential part looks like it's easy to move. It's already a negative. So I'm going to have b minus 1 over e to the b. And now I have an infinity over infinity case, so I use L'Hopital's rule. So that gives me a new limit. The derivative of b minus 1 with respect to b is going to be 1 minus 0. The derivative of e to the b is e to the b. And now when I go to plug in the numerator I just have 1, and the denominator as b goes to infinity, right, and e to infinity is going to give me infinity. 1 over infinity is 0. Okay, so this is going to be, this portion here we said was 0. E to the negative b, as b goes to infinity, remember my exponential function, b is going to infinity, but it has a negative on it. So as I go to negative infinity, the output is going to 0. 1 minus 1 is 0. Okay. E to the negative 1 I can write as 1 over e. So this is negative 1 over e. Okay. There wasn't a second piece here, so that's it. Now, one of the things we can do is see, does our result make sense? Because I got a negative value here. And remember, integrals aren't area. An integral is allowed to be negative, but I want to make sure that it makes sense. So what I could do is I could graph my function, right? 1 minus x e to the negative x. And I can see that if I start at 1 and go off, and this only goes to 10, but as I start at 1 and go out, the graph is below the x-axis. So it makes sense that I get a negative number when I integrate. Okay, so I'd say, okay, yeah, that looks good. So the integral from 1 to infinity, 1 minus x e to the negative x dx is equal to negative 1 over e. Okay. Let's look at number 5. Number 5 is really tricky because I see the infinity. I'm like, okay, that's where this has a problem. However, at 0, if you try to plug in 0, I'll get a 0 in the denominator. 0 is not in the domain either. And in fact, the denominator has a problem at 0 and also a problem at negative 1. The negative 1's not in my interval, so I don't have to worry about that. But I do have to worry about the 0. So both the 0 and the infinity are problem points. Okay. So what we can do here is we could break this up into two separate integrals. Okay. And that's, again, probably the least confusing way to do things. Or you could just have one integral where you replace the 0 with an a and the infinity with a b, and you have sort of two things going on. So it's kind of like two limits at the same time. Okay. That might be a little bit confusing, so I'm just going to do this in what I think is the least confusing way. Okay, so I'm going to write this as an integral from 0 to 1 plus the integral from 1 to infinity. Now, why did I pick 1? Well, I can pick anything I want in the middle. I'm just trying to break this up into two integrals so I only have one problem point at a time. And 1 is a nice easy number to work with. Okay. So that's why I picked 1, but you could pick 2, you could pick 3, you could pick e, pi, a billion, anything is fine, as long as it's between 0 and infinity. All right. Let's go ahead now and bring in our limits. So I'm going to have a limit as a goes to 0 from the right, the integral from a to 1 of 1 over root x, x plus 1 dx, plus the limit as b goes to infinity, the integral from 1 to b, 1 over root x, x plus 1 dx. Okay, this can be a kind of a tricky integral to work out. I've got a product, but it's in the denominator, so I can't really write this out as a nice integration by parts. So what I'm going to do instead is you know, I can try like a u substitution, okay? And I've got this square root in here. One of the things to notice about the square root function is that if I take the derivative of the square root of x, right? Remember the square root of x is x to the negative, x to the positive half. When I differentiate that, I get 1/2 x to the negative half, which is 1 over 2 root x. So if I differentiate a root x in the numerator, I'll end up with a root x in the denominator. So going the other way, if I pick my u in the u substitution to be square root of x, then this 1 over root x is going to get gobbled up by the du. So that's something that might give me a clue as to how to integrate this. Okay, so let's go ahead and try that. So I'm going to let this be. We'll not worry about the limits of integration for now. We'll come back to those after we've figured this all out. So I'm going to let u equal root x and just see where that gets me. So then du dx is 1 over 2 root x. I don't have a 2 anywhere in this integral, so I'll multiply both sides by 2. But I do have a 1 over root x dx. Okay, so all of that business can become a 2 du. And I don't have a root x, but I do have an x. So if I just square both sides, u squared is equal to x. So this is going to become the integral of 1 over, this x is going to become a u squared. And the 1 over root x dx is going to become a 2 du. Okay, this looks like something that I can integrate. And I'm just going to maybe rewrite it a little bit, just in case you're looking at it and you're like, I don't know what that is. If I just swap these, instead of u squared plus 1, I write 1 plus u squared. Oops, not dx du. I know from back in Calc 1, when we looked at inverse trig functions, the derivative of arctangent of x was 1 over 1 plus x squared. So when I integrate this, I'm going to get arctangent of u. U is equal to root x, so this is 2 arctangent of root x. Okay, so now the integration part is done. So let's go back to our definite integral and see what's going on. So I have the limit as a goes to 0 from the right of, when I integrate this, I know I get 2 arctangent of root x going from a to 1. So this is the limit as a goes to 0 from the right of 2 arctangent of root 1 minus 2 arctangent of root a. I have to be a little bit careful here and make sure I'm not forgetting the right hand, because the way I wrote this, right, I've got a chain of equals going back to my original problem, so I have to add the two pieces together. Okay, but I want to only work on one at a time. All right, square root of 1 is 1, so I have arctangent of 1 You can plug that in your calculator, but I know a 45-degree angle, like tangent of, well, tangent of 45 is going to give me a 1. So arctangent of 1 is 45 degrees, or pi over 4. The question is what's going on here. But if I just do direct substitution, arctangent of 0 is 0. Okay. You can even try it out in your calculator. Arctangent of 0 gives me 0. So I don't need to do like a L'Hopital's or anything. We just have that, right? So 2 times pi over 4 is pi over 2. Okay. So now let's deal with the other side, right? The integral from 1 to b. So I have the limit as b goes to infinity of 2 arctangent of root x from 1 to b. So the limit as b goes to infinity, 2 arctangent of root b minus 2 arctangent of root 1. And as b goes to infinity, again, it might help to think about what a graph looks like. So this is a graph of one period of y equals tangent x. Okay. Arctangent is the inverse, right? So if I plug in x values, I output y values, arctangent goes backwards. You're plugging in y values, right, and finding the x. So if I look at this and I want to say what happens as my y value goes off to infinity, right, as the y value goes off to infinity following this graph, the x value is going to approach pi over 2. And arctangent of 1 we said was pi over 4. Okay. So we have pi minus pi over 2. Pi over 2 minus pi over 2 cancel. And so this whole thing is just equal to pi. So the integral from 0 to infinity, 1 over root x, x plus 1 dx, is equal to pi. All right. Any questions on that one? Okay, that's improper integrals.